Hello, my name is Owen Dowdall.
I am Alice Monroe.
And I am Nicolas Schneider.
And we are Team 1140 from University of North Carolina at Asheville.
For this project, our group decided to take on Problem B, in which we modeled a bird going around in a circle on a bicycle wheel, as you can see in this video.
The bird is able to induce rotation in the wheel by the movement of its body.
As you can see, it appears that the bird draws itself closer to the wheel as it approaches the bottom of its rotation.
The bird also appears to straighten itself up at the top of its rotation in order to slow itself down. We were asked to model one rotation.
We chose to model the bird as a pendulum fixed to the rim of a hollow cylinder. This pendulum has a mass mb located at a length of L from the edge of the cylinder. This cylinder has a mass of mw, or m sub wheel, and a radius of r. The position of the pendulum is shown by phi. It is important to note for our model, phi is not an independent variable. Instead, it is an explicit function of theta. Since our center of mass will be changing with position, we chose to model our system using Lagrangian mechanics.
The Lagrangian is defined as the difference between kinetic and potential energy. We use the expression for rotational kinetic energy as well as the equation for gravitational potential energy. Because our distribution of mass is changing, we have to use parallel axis theorem to define a dynamic moment of inertia. Because the wheel and the pendulum moves, we don't have a constant height of the bird, so we have to define hb to use in our potential energy. Once we have the Lagrangian, we can use the Euler-Lagrange equation to derive the equations of motion. We obtain the following equation at the bottom. After differentiating I and hb, we end up with our finalized equations of motion. This equation is incredibly nonlinear, but it is generalized for any phi function.
Due to the fact that our system is so nonlinear, numerical methods had to be implemented. This meant that it was very important to approximate the constants with appropriate proportions.
In order to estimate the function phi of theta, we began by identifying 6 key criteria that phi has to satisfy. First, we assume that phi is periodic in theta, and that theta and phi have the same period. This ensures that phi has the same behavior for each rotation of theta. Additionally, we restrict the range of phi to be bound by 0 and pi over 2. This is due to the assumption that the bird never leans backwards and cannot lean forwards into the wheel. Fixing phi of 0 and phi of 2 pi to be equal to 0 ensures that the bird is in its most upright position while at the peak of rotation. From observing the video, we estimate that phi takes its maximum value after theta is greater than pi. Lastly, we assume that phi has no high-frequency terms. This is because the bird does not appear to wobble as it rotates. Using a graphical interface, we were able to experimentally determine an expression for phi, shown here, which satisfies all of these conditions. Figure 3 illustrates a single period for this expression of phi. Note that phi is bound by 0 and pi over 2, that phi is equal to 0 at theta equal to 0 and 2 pi, and that phi takes its maximum value at approximately 3.57, which is larger than pi.
We used the ODE 45 numerical solver in MATLAB. We needed to find initial conditions that minimize velocity at the end of the revolution for a given phi, while ensuring that the system completed the rotation. Through trial and error, the initial conditions were found to be 0.01 radians for theta and 0.354 radians per second for theta dot. Here's the phase plot of the solution given these initial conditions. As you can see, theta dot comes very close to 0, indicating that the wheel almost stops after one revolution. You can see that there is a maximum angular velocity at 4.88 rads per second. However, this maximum will change depending on the phi function that is being used to solve the ODE, as well as the initial conditions. We also wanted to analyze the stable equilibrium at the position theta equals pi. Due to a combination of numerical error and the fact that the center of mass changes with position, this equilibrium point is hard to identify. Figure 5 illustrates our best attempt to identify this equilibrium point. We see small, stable oscillations both in theta dot and in theta.
Using MATLAB, we were able to generate an animation in order to visualize our system with very promising results. Our model yielded behavior very similar to what we see in the video. In conclusion, our model was able to accurately describe one rotation in theta with a theta dot remarkably close to 0 at the top. However, our model did have many limitations built into it. One of the primary limitations with our model was that the pendulum would actually consume kinetic energy after the wheel made half of a rotation.
Another limitation was our approximation of phi. We did this by looking at the video and making educated guesses, but in reality we could maybe implement some numerical optimization to obtain a family of functions that yields the right solution. We also get a bit of numerical error just from using ODE 45. Another limitation was the neglection of non-conservative forces, such as friction and air resistance, as well as the fact that we are only considering a 2D projection of what is a 3D system.
That concludes our presentation. We would like to thank our faculty coach, Dr. Becky Sanft, and thank you to all of you for watching.